Our next lesson is about titrations, and you are going to be introduced to the millimole, which is written as M-M-M-O-L, like milliliter. A millimole is 1,000th of a mole. And now we know that molarity is moles per liter, but molarity can also be expressed as millimole per milliliter. I'll often be just taking it back to moles per liter just because that's what I'm most comfortable with, but just know that when we are making calculations, when we're doing titrations, sometimes using the millimole and milliliter is easier because we rarely add liters of solution when we are doing a titration, just because we add in such small amounts. So a titration, when we're adding a solution of a known concentration until the substance being tested is consumed. This is called the equivalence point. And it is when we have the concentration of our acid equal to the concentration of our base. And we graph this pH versus milliliters in what's called a titration curve. Using titration curves can help us do a few things. It can be used to determine the equivalence point in the titration, which helps us to see when those concentrations are equal to one another. It can also be used to determine the Ka of a weak acid or the Kb of a weak base, whichever one is being titrated. So 3 different kinds of titrations that we're going to investigate here is when we have a strong acid titrated with a strong base. We know those 7 strong acids and those strong bases, those hydroxides that are water soluble. We also will be looking at a strong acid and a weak base, or a strong base and a weak acid. So strong versus weak, doesn't matter which one is which. So we will look at those. And lastly, we will look at a polyprotic acid, which is unique because we will be able to see the titration curve when it loses each one of its hydrogen ions. Strong versus strong, weak versus strong, and polyprotic acids all have different looks to their titration curves. The first one that we're looking at is strong acid and strong base. And really, we need to just do the stoichiometry. So when we're looking at a strong acid like hydrochloric acid and sodium hydroxide, we know we have a double replacement reaction happening to form NaCl and H2O. So we need to be able to recognize that if we look at the parent of Na and Cl, we would have the sodium hydroxide and hydrochloric acid, and there is no hydrolysis happening here. So we are purely concerned with just looking at HCl and NaOH. So when we're looking at strong versus strong, we really need to focus on these two and looking at, do we have excess acid and is it controlling the pH, or do we have excess base and is it controlling the pH? Or are we indeed at the stoichiometric equivalence point where we have equal amounts, not a limiting reactant, and therefore at the equivalence point giving us a pH of 7. So what we're saying is that there's no equilibrium when we have two strong acid bases, because the salt that is being produced is not affecting the titration with the acid and base. And because they both dissociate completely, we're left with H plus OH minus, giving us H2O after getting rid of all of our spectator ions. And so what controls the pH is the extra, whether it's HCl or NaOH, that is continued to be added to the reaction after they have reached their equivalence point. Let's do a graph here of what it looks like when we have a strong acid with a strong base. So I'm just going to draw on my y-axis here is going to be my pH. And down here on my x-axis will be the volume of the base in milliliters. Now, this is telling us that we're titrating a strong acid with a strong base. So in our burette, there's a little tip of the burette, we have our strong base, and we're told up here that it's NaOH, and that it is 0.1 molar. And then here's our burette, and it's filled with that strong base, and it's going to titrate into our, let's do our little flask. Oh boy. And in our flask, we've got HNO3, and it's 0.2 molar. This is a strong acid. And we have, oh, it also says we have 50 milliliters of it. Okay, so we know that initially we can find our pH of this because we know that we have a concentration of just purely HNO3, which is 0.2 molar. So we can find the pH by the negative log of 0.2, right? We're given the concentration before we add any base to it. So over here we can start with, our strong acid, we're gonna start, and we would also be able to measure this with just a pH meter. Putting it right in the solution, we're starting with an acid, it's gonna be a low pH. Now as I start adding in sodium hydroxide into my acid, remember we're going to have the hydronium ions, the hydrogen ions, reacting with our hydroxide ions to create H2O. So we're going to be going towards a pH of 7. So we would see my pH begin to rise slightly, until all of a sudden it spikes. And pH rises drastically. And then we will see it start to leveling off again. So this equivalence point, what we're looking to see when all of our acid is used up, and we have a pH of 7.0. When it is completely used up and we have exactly the same number of hydrogen ions and hydroxide ions and that pH of 7. We're going to look at some different regions of this curve. Number 1, which is going to be right here, is that initial pH. Now we can determine this by looking at the strong acid, and if we're given the concentration, we can do the negative log of that initial acid, that strong acid, For example, if we were told that we had 0.1 molar of HCl, the negative log of 0.1 is a pH of 1. Here we would do the negative log of 0.2 because we were given that concentration of HNO3. Then we have point number 2, which is between the initial pH and the equivalence point, which is right here. So this is our point number 2, and it's as sodium hydroxide is added, the pH rises slowly at first, then rapidly when it nears the equivalence point. In this case, the pH is determined by how much HCl has not yet been neutralized. Because remember, we are using up our, in this case, HNO3, we have a limited quantity of it, and we're going to keep adding base. So we're using up those hydrogen ions. So in this section, section 2, we have excess acid, and that's what's going to help us find that pH. The next point, point number 3, is at our equivalence point, where we have an equal number of moles of sodium hydroxide and HCl. So they've reacted, leaving only their salt, that NaCl, and pH is 7 because the cation of a strong base and the anion of a strong acid do not hydrolyze. So it is not going to affect the pH. Remember when we looked up here, we said when we have a strong acid, strong base, and we look at the salt, we know that that salt has parents that are strong. So it is not going to hydrolyze. It has no effect on the pH. And point number 4 is after the equivalence point, which would be from here on, would be point number 4. And that's when the pH of the solution is determined by the concentration of the excess NaOH, because at this point, we have used up all of our acid, and now we have excess base. And because we have excess base, we know that that's going to drive our pH up. We know base is pH greater than 7, so because we have excess base, that's when our pH dramatically increases. So that would be the negative log of OH, which would give us the POH, and then we would need to flip it to find pH. Let's look at an example. We're going to calculate the pH when we have 0.1 molar of NaOH added to 50 milliliters of 0.1 molar HCl. Now we're going to do 2 different quantities of NaOH. I'm going to do 49 and 51, because if they were equal, if I had 50 milliliters and 50 milliliters of strong acid, strong base, they would be, since they're a 1-to-1 ratio, it would be neutralized or at a pH of 7 if there was equal amounts. So if there is less base, I would think that we would have a pH of less than 7. If we have more base than acid, I would assume that we have a greater pH than 7. So let's test our theory. When we add NaOH to HCl, we know that our products are NaCl and water. And we have a 1-to-1 ratio all the way through. And we're told our concentration of NaOH is 0.1 molar. And we're told our HCl is 0.1 molar. Remember that this is moles per liter. And we're told here that we have 49 milliliters of base and we have 50 milliliters of acid. So let's find out before, I'm going to do it before, how many moles do we have? Now remember to go from molarity, which is, I'm going to put in parentheses here, moles per liter, And this we would need to convert to liters. So I'm going to go back 3 spots, 0.049 liters. So I would need to multiply 0.1 times 0.049, 0.1 times 0.049, and I get 0.0049 moles. And I'm going to do the same thing with my HCl. So this would be 0.050 liters. So I'm going to do 0.1 molar times 0.05. I get 0.0050. So we can see here that we know that our reactants use up and then my products will gain. So I can see here that my NaOH is my limiting reactant and that I am going to use up all of my NaOH first, right? I'm going to minus 0.0049 moles to use it up. And I'm going to minus 0.0049 moles of the HCl. And there's going to be 0.0001 moles of HCl remaining. Now, if we think about this, and we could write this in scientific notation, and this is per 1 liter, so I can divide it by 1 to have a concentration of 0.0001, which in scientific notation is 1 times 10 to the negative 1, 2, 3, 4. So I can simply do the negative log of 1 times 10 to the negative 4, negative log of 1 times 10 to the negative 4 to get a pH of 4. And that's what we were thinking, was that because we had less NaOH, that we would have a low pH. Now let's check and see what happens when we have 51 milliliters of NaOH. So I kind of ran out of room over here, so I'm just going to make my same little setup with NaOH and HCl over in this margin, NaOH and HCl. So again, I'm starting with the same 0.1 molar, 0.1 molar. For my NaOH, so I'm starting with 51 milliliters. And HCl is 50 milliliters. So to find my moles, I'm going to do 0.1 times 0.051 to get 0.0051 moles. And here I'm going to do the same thing. Actually, I'm going to get the same answer as I did for my HCl, 0.0050. So obviously I can see here that my HCl is my limiting reactant because I'm going to completely use up 0.0050. So when I subtract 0.0050, I'm left with no HCl minus 0.0050. I'm left with 0.0001 moles of NaOH. So when I plug in the negative log of this in scientific notation, I can put in 0.0001 if I want to, 0.0001. The negative log of 0.0001, which is 4. But remember, that's my POH, equals 4, which is my POH. So to find the pH of the solution, I need to do 14 minus 4 to get a pH of 10. And so we can see that just that slight difference in the amount of base, I have less than my acid, I'm going to have a pH that's acidic. If I have more of the base than the acid, even just by 1 milliliter, it doesn't seem like much when I have a difference of 0.0001 mole. But that difference, having 0.001 moles of NaOH made my pH go up to 10. And if you think back to our diagram here, let's pretend like this was for our diagram. So let's say we started at the pH of, what did we start at? pH of 2. So we started way down here. And then let's say we started adding our NaOH and NaOH, and then we saw that in our calculations, having 1 milliliter less had a pH of 4, 1 milliliter more than the acid had a pH of 10, which really justifies that steep curve here, because just the difference of 2 milliliters gave us a big range. So that if they were exactly at the 50-50, we would have a pH of 7, right? Or the difference between 4 and 10 would be exactly at 7. This next one, number 2, is when we have a weak acid with a strong base or a weak base with a strong acid. So first we need to, similar to the last one, we need to find the initial pH. Now let's think about our setup on this one. So let's say I have my burette. And in this case, let's say that we have a strong base. Let's say it's NaOH that's in here. And let's say that in my flask, that I have my weak acid. And let's say that it's acetic acid. Now, remember, when I look at those weak acids, we have a Ka, and that Ka is equal to my H plus times X minus all over my molecular concentration of that acid. Because we can't, if we don't have that strong acid like we did before, we can't do the negative log of it, right? We have to take that acid and split it into our X plus, our H plus X minus concentrations. And if we don't know, which we need to solve for H plus, so remember this is when we would put in X and X. So we'd have X squared over the concentration of our acid is equal to the Ka value that we would find on our appendix D. We would solve for X and plug that in for H plus so we can find that initial pH. So if we go down here and we draw this titration curve, we have our milliliters of strong base that we're going to add. And over here we have our pH.